Hi everyone and welcome to another lecture. In our previous lectures we saw how we can define basis and what is an orthonormal basis. So today we were going to see how we can expand a vector in terms of the orthonormal basis vectors. So first you can see a diagram over here that represents the Cartesian 3D space. There is this x-axis, y-axis and the z-axis, and there is a vector called A, and this time I have not written it in terms of the bracket notation. Instead I choose the arrow because first I want to recall that what we have learned in our calculus or vector calculus courses, and then from there I want to relate the bracket notation that we are going to use in our study of linear algebra. So the first thing is, if a vector A exists in this Cartesian 3D space, we can write it like A as ax, x hat, ay, y hat, and az, z hat, where this ax, ay and az, these are the respective components of the x, y and z axis. And you know that this x, y and z's, they are perpendicular to each other. So we have written this vector A in terms of this basis vectors. So let me just write it down. And these vectors satisfy the following, that is, they are orthonormal to each other. That is, this if the dot product is 0 whenever the x and the other component other direction, that is, you are taking x over on the left side, then you put a dot, that is a dot product, and if it's y or z, this is always 0, and if it's the same thing, that is it's dotted with itself, this gives you 1. So this gives you the idea of orthogonality, this 0 thing, and this gives you the idea of orthonormality because they have a modulus of 1. So let me just get rid of these things. And this expansion over here, this is an orthonormal expansion, that is, we are using the orthonormal basis to expand this. So let's call this orthonormal expansion. So let's go down now. So the next thing we learned in our vector calculus course, that I have a vector, again ax, x hat, ay, y hat, az, z hat, and I want to find the x component or the y component or the z component. For this case, let's see the y component first. So find the y component. Now you can easily see from this expansion that this is just a y, right? But the formal way to do this is to just dot a with the y hat, or you can respectively write it as this, because dot product is commutative. And if you do that, what you have is ax, y dot x hat, ay, y dot y hat, and finally az, y hat dot z hat. And what happens because of this orthogonality, or so to say orthonormality condition, that these terms gets cancelled out and this becomes just 1. So the resulting thing is just ay. Now we want to generalize this thing in our vector spaces for more abstract objects. So let's do it. Let's write our goal first. That is, we want to generalize this idea. How can we do that? Let's say I have a vector called v that belongs to some vector space. I denoted with the capital V. So, and this V vector, this vector space is n dimensional. So let's write it down. V is a n dimensional space. So our V is a n dimensional space, and let's say since this is n dimensional, it should have n basis vectors. This is from our previous discussion, that is, this is the result we are using from our previous discussions. And this n basis vectors, let's say we represent them as follows, that is, we represent them as follows. Let's call them 1, 2, 3, n. And now for any vector v, we know that this vector can be written as a sum from n equals to 1, and let's say, okay, not n, let me choose I instead so that we don't get confused. I equals to 1 to n, and this is small v. Oops. This is small v, again vi, and I over here. So this will mean v1 1, v2 2, v3 3, and so on. The final component is just vn n. So this is how we can expand this thing, right? This is something we already know. But now let's say I want to know the jth component. That is, I want to know the jth component of V. How can I do that? Again, the idea is similar to the vector analysis results, that is, instead of the dot product, now we take the inner product. So let's first write it down, this V again. So this is sum over I equals to 1 to n. This is vi, I, and we want to know the jth component, right? So since we want to know the jth component will have a basis like this, and in this box will be our component. So we have to multiply this, let's call this equation 1. We have to multiply, or in formal sense we have to take the inner product of j with this v. So taking the inner product, jv will give us this thing. And since this is a summation over here, that is this guy, and because bras and kets are linear as well, because of this linearity property, we can just pull this summation notation out and write the whole thing as, okay, let's give it equal sign over here. So we were going to pull back this summation notation outside. We start from I equals to 1 to n again. We have our scalar component, that is v. It's not a vector, it's a scalar component. And then we have j inner product with I. But recall that these are the basis vectors, right? That is I, j are basis vectors, and they are orthonormal. They are orthonormal. That is, if you take inner product I with I, it's just 1, and if you take inner product I with j, it's 0, right? And how did we express these two conditions in a compact notation? That was inner product I with j was just delta ij. So we're going to use that over here. Okay, let me try partition as well. So let this be our partition so that we don't get confused, and use this summation thing again, vi del ij, and delta ij was either 1 or 0, right? So whenever these two indices matched, we got a 1, and whenever these two indices differed, we got a 0. So you can just use this summation notation over here, that is, it is summing from I equals to 1 to n. So this is our dummy variable here, that is the index that is being summed over. And if you expand this out, let me write a few terms so that it is easy to understand what is happening actually over here, that it is v1 delta 1j, v2 delta 2j, and so on. And there will be a term where it will be it's vj and delta jj, and then so on, and ultimately it will be vn delta nj, where n is not equals to j, right? Because n is the last component and j is something lying between 1 to n. So all of this, that is this one, and all the terms in these dot dots will get cancelled out, because delta 1j is equals to 0, that is delta 1j is 0 when j not equals to 1, and delta jj is just 1, right? So using these things, we finally have, this is vj times 1, which is just vj. So this is the thing we wanted to evaluate, and finally we can write that j v is equals to v of j. This is how we can find the components of a vector. Now let's try to look at some examples. So examples. So we derive this result as a general. Notice that we haven't specified anything about how these vectors are represented, that is this v's, whether it's a column vector or it's a matrix. So we haven't specified anything. So this is a general result. Now how you interpret this inner product will depend on what you are dealing with. So let's try to see some examples first. Let's say you have a column vector a prime. Okay, let me use another color. So the column vector will be denoted with a prime. It's just, let's take a 4-dimensional case, right? 1 2 3 4. Let's take this. And if you recall your lectures, that this can be written as 1 1 2 2 3 3 4 4, where 1 is denoted as 1 0 0 0, 2 was represented as 0 1 0 0, and so on. So these vectors are orthonormal to each other, and I want to know the third component. What is the third component of a prime? That is, I want to know what is 3a. So the third component word might be a bit weird, because here you can, this is a summation, so you can obviously change the order of the summation. So let's say by third component we mean that the component that is appearing in front of the third basis vector, that is the basis vector denoted as 3. So this is easy, right? You just take the inner product, 1 3 1 2 3 2, then 3 3, oops, I forgot to write 3 over here, and 4 3 4. So this is just giving you 1, and all of this will go away because all of them are 0. And also notice that you could also write, instead of 3, then the sandwiching thing, instead of that you could write 3 times 3. This is times the ordinary multiplication, scalar multiplication, because whenever you have a bra and a cat and you sandwich them, you always get a number, and when numbers are multiplied, they are commutative, that is, the order doesn't matter there. So this is just 3. And now finally we want to show that these vectors were actually orthonormal, because just take this inner product of 1 and 2, right? So let's take 1 and 2. Again, this is something you should be able to recall from your previous lectures. That is a very basic algebra of the bracket. So it will be just this, and it will be 2, right? So there should be a 0 above, and you can see that 1 multiplies 0 is 0. So this is similar to a matrix multiplication, and you can evaluate this and get a 0. Similarly, you can even prove that, let's say I have some matrix B and it is like A, B, C, D. I'm considering a 2 cross 2 case, but you can always take n cross n cases, and this was written as A1, B2, C3, D4, right? And to get any element, that is the row and the column, you have to specify the row and the column of this column of the matrix, right? Okay, I forgot to put a cat over here. So this one was represented as 1 0. Oops, sorry, 0 0 0. This 2 was represented as 0 1 0 0, and so on. So to know any component of the matrix, again you can use the idea of the inner product to your advantage. So how can we do that? Let's say I want to know what is B11, that is the first row and the element from the first row and first column. So if you take an inner product with the first basis vector, this will just give you A, right? And why we are saying that these matrices are orthonormal? Well, remember that any basis vector I and j was just delta ij, right? So why we are saying this, that these matrices are orthonormal? Let's try to see it. So let's try to find, okay, let me choose another color. I will just stick with green. So if I do 1 and 1, remember that this one, that is the bra of 1, is coming from the adjoint of the ket 1, that is bra of 1 was represented as the dagger operation of the ket 1. That is, first you have to take the transpose, and then you have to use the complex conjugation in each and every element. So here we are just dealing with the real entries, so there is no complexity of the complex conjugation. So let's just write this straightforward thing down. We will have 1 0 0 0, and here we should have another 1 0 0 0. Now the question is, that is the bigger question, is this just matrix multiplication, just standard? Because when you take an inner product, you are supposed to get something that belongs to a field, that is a scalar. But when you multiply two matrices with the rules of standard matrix multiplication, you get another matrix, right? So now, however bizarre this may seem, this is not standard multiplication over here. So when you write this thing like this, this is not a standard matrix multiplication, rather it will be the trace of them. Okay, let me just write it down. It will be the trace of these two matrices. That means after you multiply them, so let me put trace over here. So let's try to see what happens. So for now, take this definition as granted. In the later lectures, when we deal with linear operators, we will prove that that whenever you multiply two matrices, that is, you want to take their inner product, that will result in the trace of the matrix multiplication product. So I'll write it down again, but let's try to evaluate this trace now. So trace of this will be just 1 0 0 0, is it? Yeah. So this is 1, okay, that's correct. This is 0 0, okay, yeah, this is correct. And if you just take the trace, this is 1, so that's good. And what about 2 1? So this was, again, you have to write the trace, and you put a 1 over there because that's how 2 was represented. Okay, this seems a bit so let's write this thing again, all the matrices again. Oops. Now multiply them and evaluate the trace. If you multiply them, you can see that this is first entry is 0, second entry is obviously 0, third and fourth are 0 as well, and the trace is just 0. So this is nice, and you can eventually show that this 3 and 4 and all of these things, that is 1 2 3 4, all of these objects are satisfying this property. That is, when they are dotted together, they are giving you 1, but if they are dotted with a different vector or a different ket, they are giving you 0. So for a matrix, when you represent your vectors with matrices, the inner product will correspond to a trace of the product itself. So let's try to write it down. Let's say, so this is something to keep in mind. So something to keep in mind. A matrix is denoted by, let's say, alpha. This is some matrix, and we are denoting with this alpha ket, and another with beta. This is another matrix. If this is true, then alpha and beta's inner product will be given by the trace of alpha beta. And you know that trace has another property, that trace of AB is equals to trace of BA, right? Where AB is some matrix, and here this product is just coming from the standard matrix multiplication. So you can also write it like this. And we will prove why this is so when we discuss something called linear operators. So this will be it for today, and thank you.